like to talk about some of the problems that the human race is facing. Some of these problems are global, some are national, some are local. But they're all tied together. They're tied together by arithmetic. The arithmetic isn't very difficult. And what I'd like to do is I'd like to try to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So we're going to talk about the arithmetic of compound interest, of inflation, of steady growth. This is the arithmetic of the exponential function. Now, the exponential function is used to describe the size of anything that's growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, ordinary, steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now the longer time is called the doubling time. We need to know how you calculate the doubling time, and fortunately it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. And so our example of 5% per year, when you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Now you might ask, well, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So you can see it's very logical, but it's not important to remember so much where it came from. It's important to remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things had been growing 8.7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says the prison population could double in 8 years, you say, well, my heavens, what's happening? And the answer is 8.7% growth per year. Notice when you express it as a percent, most people don't have any real understanding what it means after 1 year. But express it in terms of doubling, people begin to understand. And the journalists use this all the time. State court appeals double in a decade. Well, what's the growth rate that gives you doubling in a decade? You take that number 70, divide it by the 10 of the decade, you get 7. 7% per year gives you doubling every decade. But could you write a headline saying state court appeals growing 7% per year? That wouldn't get anyone's attention. If you want to get people's attention, you have to talk about doubling. And I think it's very important that we convert every percent growth rate we see in any news story, convert it into a doubling time so we can get an appreciation of what's happening. But now, do you really know what 7% per year means? Let's take an example from Colorado. The cost of an all-day lift ticket at Colorado's Vail ski area has been growing 7% per year ever since Vail first opened in 1963. At that time, you paid $5 for an all-day lift ticket at Vail. But it's been growing 7% per year ever since. So by 1973, the cost had doubled to $10. By 1983, it was $20. By 1993, it was over $40. And if this continues, by the year 2003, you will pay $80 a day for an all-day lift ticket at Colorado's Vail ski area. Now, did you know that that's what 7% per year means? Most people don't have any idea about this. Let's take another example of 7% per year. Let's take an example of compound interest. Suppose I put $1 in the bank at 7% compound interest. How large would the bank account be in 300 years? Well, you take the 70, divide by 7, you get the doubling time is 10 years. You divide 10 into 300, you find it's going to double 30 times. And so the size of our bank account will be a number of dollars equal to 2 raised to the power 30, which means a chain of 32s multiplied together. And the answer is it's a little over $1 billion. And your interest would be coming in at the rate of $2.38 per second. That's what 7% means. Let's look at another example of inflation. In the year 1626, Manhattan Island was purchased from the Native Americans for $24. If that $24 had been put in a savings account, what interest rate would be required the dollars in the account today would be equal to the assessed valuation of all the taxable property in New York City. And the answer is slightly over 6% per year would give you a transition from $24 in 1626 to the assessed valuation of New York City today. That's what we have with compound interest. That's what we have with inflation. So let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. Two doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512, and in just 10 doubling times, it's 1,024 times its initial size. Well, you can see if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Well, let's look now at the enormous numbers you can get with just a modest number of doublings. Legend has it that the game of chess was invented by a mathematician who worked for a king. And the king was very pleased. He said, "I want to reward you." And the mathematician said, "My needs are modest. If you'll just take my new chessboard and on the first square place 1 grain of wheat. On the next square, double the 1 to make 2. On the next square, double the 2 to make 4. We'll just keep doubling till you double for every square. That will be an adequate payment." Now we can guess that the king thought, well, this foolish man, I was ready to give him a real reward. All he asked for is just a few grains of wheat. Well, let's see what's involved in this. We note that there are 8 grains on the 4th square. Now I can get this number 8 by multiplying 3 2's together. It's 2 times 2 times 2. It's 1 2 less than the number of the square. Now that follows in each case. So on the last square, we'd find the number of grains by multiplying 63 2's together. Now let's look at the way the totals build up. When we have 1 grain on the first square, the total on the board is 1. We add 2 grains, that makes a total 3. We put on 4 grains, now the total is 7. Well, 7 is a grain less than 8. It's a grain less than 3 2's multiplied together. 15 is a grain less than 4 2's multiplied together. Well, that continues in each case. So when we're done, the total number of grains will be 1 grain less than the number I get multiplying 64 2's together. And my question is, well, how much wheat is that? You know, would that be a nice pile here in the studio? Would it fill the building? Would it cover the county to a depth of 2 meters? How much wheat are we talking about? The answer is it's roughly 400 times the 1990 worldwide harvest of wheat. That could be more wheat than humans have harvested in the entire history of this earth. And you say, well, how did you get such a big number? And the answer is, it was simple. We just started with 1 grain, but we let the number grow steadily till it had doubled a mere 63 times. Now, there's something else very important. We should note that the growth in any doubling time is greater than the total of all of the preceding growth. For example, when we put 8 grains on the 4th square, the 8 is larger than the total of 7 that were already on the board. When we put 32 grains on the 6th square, the 32 is larger than the total of 31 that were already on the board. Every time the growing quantity doubles, it takes more than all that you'd used before. Now let's translate that into the energy crisis. It's an ad from the year 1975. It asks the question, could America run out of electricity? America depends on electricity. Our need for electricity actually doubles every 10 or 12 years. Now that's an accurate reflection of a very long history of steady growth of the electric industry in the United States. Growth at a rate of around 7% per year, which gives you doubling every 10 years. Now, with all that history, they expected the growth would go on forever. Now, fortunately, it stopped. Not because anyone understood this arithmetic, it stopped for other reasons. But let's ask, what if? Suppose the growth had continued. Then we would see here the thing we just saw on the chessboard. In the decade following the appearance of this ad, in that 10 years, the amount of electrical energy we would have consumed in this country would have been greater than the total of all of the electrical energy we had ever used in the entire preceding history of our nation. Now, did you realize that anything is completely acceptable, a 7% growth per year, could give such an incredible consequence in such a modest period of time? Now, that's exactly what President Carter was referring to in his speech on energy. One of his statements was this. He said, and in each of those decades, more oil was consumed than in all of mankind's previous history. Now, by itself, that is a stunning statement. But now you can understand it. The president was telling us a simple consequence of arithmetic of 7% growth each year in world oil consumption, and that was the historic figure up until the 1970s. Now, there's another beautiful consequence of this arithmetic. If you take 70 years as a period of time, and note that that's roughly one human lifetime, then any percent growth continued steadily for 70 years gives you an overall increase by a factor that's very easy to calculate. For example, 4% per year, you find the factor by multiplying 4 2's together. It's a factor of 16. Now, a few years ago, one of the newspapers here in Boulder, Colorado, quizzed the 9 members of our Boulder City Council and asked them, what rate of growth of Boulder's population do you think it would be good to have in the coming years? Now, the 9 members of the Boulder City Council gave answers ranging from a low of 1% per year. Now, that happens to match the present rate of growth of the population of the United States. We are not at zero population growth. The number of Americans is increasing each year by about 2.7 million people. No member of the Boulder City Council said Boulder should grow less rapidly than the United States is growing. Now, the highest answer any council member gave was 5% per year. Well, you know, I felt compelled. I had to write them a letter and say, did you know that 5% per year for just 70 years, and you know, I can remember when 70 years used to seem like an awful long time, but it doesn't seem so long to me now. Well, that means Boulder's population would increase by a factor of 32. That is, for today, we have 1 overloaded sewer treatment plant. In 70 years, we need 32 overloaded sewer treatment plants. Now, did you realize that anything as completely all-American as 5% growth per year could give such an incredible consequence in such a modest period of time? Our city council people had zero understanding of this very simple arithmetic. Well, a few years ago, I had a class of non-science students. We were interested in problems of science and society. We spent a lot of time learning to use semi-logarithmic graph paper, which is printed in such a way that these equal intervals along the vertical axis each represent an increase by a factor of 10. And the reason one uses this special paper is that on this kind of paper, a straight line represents steady growth. Now, we worked a lot of examples. I said to the students, let's talk about inflation. Let's talk about 7% per year. It wasn't this high when we did it. It's been much higher since then. Unfortunately, it's lower now. And I told the students, you have about 60 years life expectancy ahead of you. Let's see what some common things will cost if we have 60 years of 7% annual inflation. Well, the students found that a 55-cent gallon of gasoline will cost $35.20. $2.50 for a movie will be $160. The $15 sack of groceries that my mother used to buy for $1.25, that'll be $960. A $100 suit of clothes will be $6,400. A $4,000 automobile will be $250,000, and a $45,000 home will be nearly $3 million. Well, I gave the students these data. These came from a Blue Cross Blue Shield